Hello there, my name is Tomas. I'm a co-founder of the Passivhaus Academy, and I'm going to make a presentation to you now concerning the retrofitting of New York City building stock. I'm first of all going to give an overview of Passivhaus Academy. We'll give an introduction to the EnerPHit standard. We'll talk about cost optimality for retrofitting. Following that, we'll show you an EnerPHit case study, and then we'll have some closing remarks. Passivhaus Academy has been very active in the United States since 2009. We offer three services. The first of these services is Passivhaus certification, and you can see some of our projects here. We're also very much involved in Passivhaus consulting, especially on tall buildings and retrofit projects. And we're also active in the training arena, and we've trained hundreds of Passivhaus designers and Passivhaus tradespeople. The EnerPHit standard is the retrofit standard developed by the Passivhaus Institute. The various metrics that you have to hit in order to be certified as an EnerPHit project are presented here. There are maximums for heating demand, for cooling demand, primary energy or source energy, air tightness, and overheating. You can certify according to these criteria, or you can certify your building according to components. Now, New York is located between a cool temperate climate and a warm temperate climate, and a summary of the U values for opaque and transparent elements are presented here. And I'm summarizing on the next page in IP units. So you can see here the kind of R values that we need depending on whether the installation is on the exterior or interior. Also the maximum U values for windows, which range between 0.15 and 0.18. We also talk about solar heat gain coefficient with a view to maximizing solar heat gains, but without a risk of overheating, and also the minimum heat recovery rate from ERVs, which should be 75%. Despite all those components and standards, we must model every project in the Passivhaus planning package, and the PHPP is a bit like a sound desk where you've got levers for insulation, for window performance, for ERV efficiency, and the objective is to use the PHPP as a design tool to hit the sweet spot for your retrofit project. The next most important thing is to consider how cost optimal are the various retrofit measures that you're going to employ. And what we want to do is we want to get from low efficiency buildings up to high efficiency buildings. And you have a choice whether you can do this all at once in one complete retrofit to head towards nearly zero energy buildings, but there will be a lot of challenges involved in doing it in one fell swoop. And often it may be better, or it may make more sense to do it as part of an overall refurbishment plan and to do it step by step by step. And this is the concept that we're exploring as part of the EnerPHit project. The Intergovernmental Panel on Climate Change, IPCC, is, I suppose, a global policy on energy efficiency and involved over 100 government signatures. And the lady who wrote the chapter dealing with buildings is Diana Urgevor-Satz, and she has warned us to be very, very careful to avoid what she calls shallow retrofits. If we engage in retrofitting which is not aggressive enough, we're going to lock in an inefficiency into buildings which the building will be burdened with for generations. So it's better if you've got a limited budget to do just perhaps one part of the project, but to do it to the most cost optimal way. If we look at economic feasibility, imagine we have two scenarios. Option A is the cost to conserve a kilowatt hour of energy, and option B is the cost to buy 1 kilowatt hour of energy. Well, if option A is cheaper than option B, then option A is a no-brainer, and we should definitely engage with that measure. And I'll explain this a little bit further in the subsequent slides. The IPCC uses this indicator, the cost to conserve energy, and in the blue circle here we can see projects which don't save very much energy. So on the horizontal axis you can see they're saving around 20% of energy compared to a baseline. But on the vertical axis you can see the cost of conserved energy, and they range from projects which are not so expensive to projects which are quite expensive. In the brown box below, we see projects which are all quite low cost in terms of conserved energy, but they range from very little savings on the right towards very aggressive savings on the left. And this is where we want to be with our EnerPHit projects. So what we want to be is in the lower left-hand corner here. We want to have projects which are fantastic in terms of energy saving, but also very cost efficient. The Passivhaus Institute developed the EnerPHit standard using prototype projects like the one we've got here in front of us. In this case, they reduced the space heating demand on this project in Germany by a staggering 85%, using the measures on the right hand side here, such as insulation, windows, and airtightness with heat recovery ventilation. So what PHI did was they developed a methodology to work out the cost of conserving energy for each individual measures. So you can see here the cost to save energy using wall insulation, floor insulation, window replacement, and so forth. And then they compared that to the cost to purchase a kilowatt hour of energy using oil or gas. And you can see here the four measures in the blue box here are also standalone economically viable. It's actually cheaper to conserve a unit of energy in this case than it is to purchase a unit of energy. The three factors on the bottom, which include window replacement, which I'll come back to in a few moments, are actually on a standalone basis more expensive in terms of conserving energy than to purchase a unit of energy. But when you combine these 7 measures cumulatively on one project, such as the photograph in the top right hand corner, they all average out exactly at the same cost as it is to conserve a unit of energy. So some measures are on an individual basis very, very cheap to do, and other measures are more expensive, but on average they come in at the cost optimal approach. This has all been done as part of a very exciting research project called EnerPHit, and we'd love you to visit our website, enerphit.eu. And as part of that project, we've retrofitted numerous projects around Europe, including this one by La Maison Passif in France. And you can see here they have developed a step-by-step retrofit approach here, going from 92 kilowatt hours per square meter per year down to 16 kilowatt hours per square meter per year, exceeding in fact the EnerPHit standard. And this is from 2013 to 2018. We can look at that in IP units now, where the space heating demand goes from 29 kBTU per square foot per year down to 5 kBTU per square foot per year. But the key thing is that every step is done to the cost optimal basis. And the factors used to measure cost optimality are listed here. So what is the cost of the individual measure? If there's any maintenance costs, are there any subsidies? What's the life of the product? For example, wall insulation might last 50 years, whereas roof insulation might last 100 years, depending upon the setup. How much energy are you saving? What is the interest rate? What is the duration of borrowing? And what is the energy price? And if we put all these factors into the new version of PHP, which is PHP 9, it'll basically tell us what the cost to save 1 kilowatt hour of energy is. And if we zoom in on these two little figures here in the red circles for the French project, in this case the cost to save a kilowatt hour of energy is 18 euro cent, compared to the cost to buy a kilowatt hour of energy, which is 25 euro cent. So in this case, the upgrading measures that La Maison Passif were proposing are entirely valid when it comes to economics. What if we go back to New York now and we look at the option of upgrading from, let's say, single glaze windows to double glaze windows? This data is provided by Clearwall, which is a company supplying certified passive house windows to the US market. And we've got costs per square foot here for PVC options and for aluminum options. We can compare those costs then with triple glazing to the passive house standard, and you might be quite surprised here. There's quite a low uplift in terms of cost, because many of the companies, including Clearwall, are producing at such a volume that the differential between double glazing and triple glazing is actually only about 10%. So on the face of it, it won't surprise you that passive house standard windows are more expensive. But if we look at the cost optimality of those windows, the blue column here shows the cost to conserve a kBTU using the double pane windows, whereas the red column is the cost to conserve a kBTU using the Passivhaus standard windows. And you can see here, not surprisingly, that the Passivhaus standard is more cost optimal. And the same pertains to the aluminum windows. We have the green and orange columns here for double pane and triple pane respectively. These are more expensive than the cost to purchase a kBTU of energy, but as we saw from an earlier slide, windows are more expensive in terms of cost energy reduction than compared to wall insulation or roof insulation. Another factor we have to consider is the comfort provided by different glazing systems. In wintertime, we want to make sure that the surface temperature of the glass is above 62 Fahrenheit. And then in this table here, we are comparing in the first column on the left, single pane windows with Energy Star double pane and Passivhaus triple pane windows. In the middle column, we have the surface temperature on the interior of the glass in the average winter low temperature. And you can see in this case that the Passivhaus window exceeds our comfort criterion, so that provides good comfort for the occupants. In the right-hand most column then, we have the polar vortex of January 2014. So this is when the severe low temperature hit New York, and again we can see that the Passivhaus window still would provide adequate comfort for the residents in this case. So for comfort, we need to avoid single pane windows, and we should also try to do better than high performance double pane windows if we want to maintain comfort in even the most extreme weather conditions. Okay, let's have a look at a case study. This is a 20-story EnerPHit project in Germany, which was retrofitted to a very poor condition. You can see the air tightness they got was 0.2 air changes per hour, so an incredible performance in terms of comfort. This building was reskinned completely, so they took the facade off, they rearranged the spaces internally and then put on a new facade, and also put on some very nice thermally separated structural balconies. The building was also given a facelift, so the rather sad entrance lobby here on the left was replaced by this lighter, brighter design. So the occupants had much improved comfort, dramatically reduced energy consumption, and also greatly enhanced in terms of aesthetics. The building is now mechanically ventilated. It has two very large ventilation systems which provide fresh air throughout the whole structure. When we're considering retrofits like this, it's worthwhile to consider off-site construction as much as possible. This is another very exciting project undertaken in the UK recently, and they used a German panelized system, in this case made by a company called Gumpen Meyer, and you can get a sense from that of the level of accuracy and efficiency that they're going to achieve with those. When we're thinking about the scale of refurbishment, we need to think, are we going to just do one facade? Are we going to do an entire block? Or are we going to do an entire region in a city? So we need to think about the scale at which we're going to apply these principles. We also need to think about construction detailing. So on the left, we have a poor window install detail. On the right, we have an improved detail. And we see this in this 3D view here, where we've got a window which is disconnected from the insulation on the inside and is sitting on a brick windowsill, and so the thermal bridge coefficient here in this case is extremely high and will cause a lot of energy loss and also discomfort and possibly mold. If we can connect the window to the insulation layer, as we see here, and also sit the window on an insulated windowsill, we can actually reduce the heat loss in this case by almost 3/4. So if you're going to do it right. When we are putting projects out to bid, we like to insist that the contractors engage in a training program, and in so doing, you're less likely for contractors to include a fear factor in their bidding price. And we would encourage you to use certified Passive House tradespeople and certified Passive House designers who've been through the program, such as the one we provide, which ensures that they have a really good exposure to the critical issues that you'll be encountering on your project. So in terms of closing remarks, Passive House has been identified as an exemplary standard in New York. We can see here from this graphic prepared by the Urban Green Council. So Passive House is definitely something for the future in New York. In terms of mapping a way forward, we have the policy backdrops provided by IPCC and the Mayor's Office of Sustainability. We have the scientific rigor provided by the EnerPHit standard. We have the planning tools through the PHPP software, and we can be assured of quality if we use accredited Passive House tradespeople and Passive House designers. The next step, of course, is to engage in some pilot projects, which we hope will be underway in New York very, very soon. Passive House Academy can help in this regard. We can provide energy modelling in PHPP, we can do construction detailing and thermal bridge analysis. We can also train up your design and contractor team, which can help to assure that we have good quality, and we can also certify the project as an EnerPHit project. So thank you very much for your attention. I hope that was interesting, and the closing message is whatever you do in terms of retrofit, even if it's limited to one facade of a building, make sure that you do it right. Thank you.